Hello everyone, and thanks for watching Edupedia World Videos. In this video we'll begin a new unit called Vector Algebra, and we'll start with our discussion of vectors. Now the formal definition of a vector is any quantity which has both magnitude and direction. So let's first of all look at why there is a need for vectors. If you take, let's say, an object which has a mass of 3 kgs, and you take another object which has a mass of 4 kgs, and you combine them, you get a resultant object which has a total mass of 7 kgs. There is no exception to this rule, right? Which means that when you're talking about the mass of an object, now mass, velocity, speed, temperature, these are all what are called physical quantities. So the mass of an object is a type of physical quantity, and the physical quantity mass always obeys the rule that 3 kg plus 4 kg gives me a total of 7 kg. Right, so this is the rule for mass. Let's look at a few other quantities like this. Let's look at the distance traveled by a body. So what is 3 meters plus 4 meters? If I move from point A to point B and I travel a total distance of 3 meters, then I go from point B to point C and I travel a total distance of 4 meters. What is the total distance I have traveled from A to C? Well, that is 7 meters. Right. So the distance traveled is also a physical quantity which obeys a similar rule that to add two such physical quantities, you simply add their numerical value. Right. 3 kg plus 4 kg always gives me 7 kgs. 3 meters plus 4 meters always gives me 7 meters if we are talking about the distance traveled. Now let's talk about another quantity which is not the distance, but it's something you've already learned before, the displacement. Broadly speaking, the displacement would be the difference between the final position and the initial position. Right. So let's say you go from point A to point B, which is 3 meters away from A. In that case, the displacement would be 3 meters. Now, the definition of displacement is basically the distance between the final and initial point. So instead of this way, if I choose to go from A to B by some complicated path like this, the distance traveled will be different, but the displacement would still be 3 meters. Right, because the displacement is basically the distance between the initial point and the final point between A and B. And that is the same regardless of how you go from A to B. Right. For a moment, let's just assume we go in straight lines. So we have the point A and we have the point B, which is 3 meters away from A. Let's say we also have a point C, which is 4 meters away from B. Yeah, so let's say we have the point C, which is 4 meters away from B, and B is 3 meters away from A. So once I go from A to B, the total displacement is 3 meters. When I go from B to C, the total displacement is 4 meters. So let's take the other displacement, 4 meters. Well, what happens when you add them up? What happens when you add, now we are not talking about distance, remember, now we are talking about displacement. What happens when you add a displacement of 3 meters to a displacement of 4 meters? That means going from A to B and from B to C. What is the net displacement? Well, in this case, the net displacement would be the distance between A and C, and we know from Pythagoras theorem that that's 5 meters. So we get this unusual result for displacement 3 meters plus 4 meters is equal to 5 meters. But hang on, even that's not always true. What if you have another point D, which is 4 meters away from B, but it is along the same direction as A to B? In that case, if you take a displacement of 3 meters, this is, by the way, AB plus BC and total of AC. But if you take 3 meters AB plus a 4 meters displacement of BD, Then you get a total displacement AD, but now it obeys the normal rule 7 meters, because now these two are the same line, so the distance AD is a total of 7 meters. That's not it. What if B, what if there was a point E which was at a distance of 4 meters from B but in the opposite direction? So let's say this was the point E where the distance EB total was 4 meters. In that case, you would have 3 meters which was AB plus 4 meters which would be BE, and that would give me a displacement of minus 1 meters if we're talking about AE, right? Because it's in this direction. Yeah. So we see that displacement is a physical quantity which follows a somewhat different rule. When you're talking about distance, 3 meters plus 4 meters is always 7 meters. When you're talking about mass, 3 kg plus 4 kg is always 7 kg. But when you're talking about displacement, 3 meters plus 4 meters could be 7 meters, could be 5 meters, could be minus 1 meter, or in fact could be many other different things. So these type of quantities are called displacements. My bad. These types of quantities are called vectors. Displacement is a type of vector, and you can see that the difference is because of the angle between AB and BC. Basically, it depends on the direction of BC or BD or BE. But once we decide AB, what actually depends on is the angle. So this is where direction comes in. So these vectors, they're generally represented by arrows because the magnitude and direction are both important, and they are only uniquely specified by both magnitude and direction. For example, a displacement of 3 meters in this direction is very different from a displacement of 3 meters in this direction, even though the physical quantity 3 is the same, but the direction is different. So a physical quantity that is uniquely determined not just by what is called the magnitude, 3 would be called the magnitude, meters would be the units, and the arrow would denote the direction. A physical quantity that is not just determined by its magnitude, but it also needs its direction to be uniquely specified is called a vector. Other examples of vectors could be velocity, force, and so on. Right? These are all vectors. Now, vectors obey different rules of addition and multiplication and so on, which we'll learn in a little bit detail in a later video. But right now, let's look at how we can actually uniquely specify a vector. Right? So generally, to specify a vector, just like to specify a point in space, it is good to have a frame of reference or an axis of reference in this case. So the first thing we do is denote our xy axis. So this is the x-axis, this is the y-axis. Right, now let's go to a previous case. This was A, this was B, C, D, and let's forget E for now. Right, so how would you characterize these displacements? AB is a displacement, BC is another displacement, BD is another displacement. AB is a displacement which has a magnitude 3 meters, and both these displacements have magnitudes of 4 meters. Well, so the first thing we do is we make our axis, and we can choose our axis to be anything, right? We can choose any direction to be the x-axis, and from that we can determine the y-axis. So we choose the x-axis, let's say to be the direction along AB or along the horizontal direction. Then AB would simply be represented in this way. So it would be a vector going from A to B, a line segment going from A to B with an arrow, and its magnitude would be 3 meters. So what we generally do when we are drawing vectors on a coordinate axis is we say the length of the arrow the length of the segment, not the arrow, is linearly proportional to the magnitude. Which means if AB denotes a displacement in the positive x direction of magnitude 3 meters, then a displacement in the positive x direction of magnitude 6 meters has to be twice the length. and a displacement in the positive x direction of only 1 meter has to be 1/3 the length of AB. So when we are drawing vectors on this coordinate axis, we will assume that the length of the line segment is proportional to the magnitude of the vector. Also, the 2 points and the line joining them determine the direction of the vector, and the arrow determines which side it points. For example, this would be AB going from left to right. You could also have a displacement CD which goes from the right to the left. These displacements have the same magnitude, they are also along the same line, but they still have different directions because one points along the positive x direction and the other points along the negative x direction. Right. Similarly, if this is AB, which is 3 meters in length, then we can draw BC as well. Once you decided this is AB, BC will be perpendicular to this like this. We can just draw it here. And if this is a length of 3 units, then this has to be a length of 4 units to signify that it's a displacement of 4 meters. Right. So the general way we specify these vectors is in terms of their magnitude and direction. But how do you specify the direction? To specify the direction, you first need an axis. Once you have an axis, you specify the direction by specifying the angle made with the x-axis. And by that, you already know this, we mean the angle made with the positive x-axis in the anti-clockwise direction. So the first quadrant gives us positive values. Right. So for example, you say there is a vector of magnitude 6 meters and it makes an angle of 45 degrees with the x-axis. So that vector, since it's 45 degrees, it lies in the first quadrant. So it would be a vector like this, which would have a length twice the length of AB, and it would make an angle with the positive x-axis to be 45 degrees. What is AB? AB is a vector of magnitude 3 meters and angle 0 degrees with the x-axis because it's parallel to the positive x-axis. BC is a vector of magnitude 4 meters and angle 90 degree with the x-axis. BD, a vector of magnitude 4 meters, angle 0 degrees with the x-axis. The angle with the x-axis is generally will be a number between 0 and 2 pi. Right. Or you could have it in any other interval, but any addition of 2 pi gives you the same angle. So these are the two things that uniquely determine a vector when you're talking about a representation in terms of the magnitude and the angle made with the axis. Right. And from now on in this course, I will refer to this as the magnitude direction format. Magnitude direction format is one way of representing the vector. In that way of representing the vector, you give the magnitude of the vector and the angle made with a particular direction. There's actually another way to represent a vector uniquely, and that is in terms of its components. So let's look at that now. I'll just rub a little bit of this. So what we are doing right now is we learn two different representations of a vector. One will be the magnitude direction representation, wherein if you are given a vector in a question, you will be given something like a vector of magnitude 10 units making an angle of 60 degrees with the x-axis. That completely specifies the vector, the magnitude and the angle. Another way to specify a vector would be in terms of its components. Right. So let's just look at this vector, a vector of magnitude 6 units. I'll forget meters now because meters generally means displacement, but units could be anything. So we want a vector of magnitude 6 units and angle with the x-axis to be 45 degrees or pi by 4. We can represent the same unique vector using the x and y components. So we will basically break this vector into two separate vectors. Now we'll discuss in detail the addition of vectors in a later video, but for now we just need to know that AB plus BC gives us AC. That's sort of what addition means, right? We'll learn that in detail later, but this is all that you need to know right now about addition. So this vector, and for the sake of just convenience, I'll draw it with one endpoint at the origin. Right? That doesn't necessarily make a difference because in defining a unique vector, we don't define where it starts from. In fact, it doesn't start from anywhere. A displacement of 6 meters east is a unique displacement. It doesn't matter whether you start from this point or you start from this point, right? The vectors will still be the same. So for the sake of convenience, we'll put one point at the origin. So we have 6 and we have 45 degrees. Now we can represent this vector as the sum of two vectors, this vector and this vector, right? If you go in this direction and this direction, this is the net displacement. If these are the two forces, this would be the net force, and so on. So these are the two components of the vector. What are the components? Well, that's quite easy. Anything, if it has 7 components, that means when you add the 7 things, you get that thing. So if we break this vector into two components, let's say A and B, remember vectors are represented with an arrow on them. If we represent this vector as two components, that means this vector, we'll call it C, is equal to the sum of these two vectors A and B, right? Now we can represent the vectors A and B even further. We can simplify them. Let's call a vector which has a magnitude 1 unit in the x direction, we'll call it I cap. And a vector of magnitude 1 unit in the y direction, we'll call it j cap. By the way, just a little bit of terminology. Any vector with a magnitude of 1 is called a unit vector. Unit vectors, instead of an arrow over them, are generally represented with a hat over them. So C with an arrow over them would be the vector C, but C with a small hat sign on top of it would be a unit vector. And by convention, the unit vector along the x-axis is called I and the unit vector along the y-axis is called j. Now let's look at what these two lengths are. If this is 6, this is 6 cos 45, that is 3 root 2, and this is 6 sin 45, also 3 root 2. So a vector of magnitude 1 in the x direction is I. What is a vector of magnitude 3 root 2 in the x direction? 3 root 2 I, where 3 root 2 is the magnitude and I is the unit vector which denotes a direction. That's the purpose of a unit vector. It denotes the direction. So a vector can be written as 3 root 2 I because it is 3 root 2 times this unit vector which represents the I axis. Similarly, B is, this should be 3 root 2, sorry, 3 root 2 J, because it is a vector of magnitude 3 root 2 and J is this vector in the vertical direction. And since C is the sum of these two vectors, we can write, I'll just rub a little bit here, we can write this vector as 3 root 2 I hat plus 3 root 2 j hat. Sometimes they refer to as I cap and j cap as well. Now this tells me the x component means the component of this vector along the x direction is 3 root 2 I hat, and the y component is 3 root 2 j hat. Now the important thing here is, just like the magnitude and the angle uniquely determine a vector, two different vectors will always have either different magnitudes or different angles. Similarly, the x and y component uniquely determine a vector. If the x component is 3 root 2 I cap and y component is 3 root 2 j cap, then the vector has to be a vector of magnitude 6, making an angle of 45 degrees. AB will have its own x and y components. BC will have its own x and y components. BD will have its own x and y components. Now we'll look at all of this a little bit more generally. And basically what we are doing is we are taking two representations of vectors. One is the magnitude and direction, and the other is the x and y components. Oh, I'm sorry. So to uniquely specify a vector, you can say, well, the vector has a magnitude of 20 units and an angle of 140 degrees with the x-axis. Or you can say the vector has an x component of 30 root 2 I cap and a y component of 50 j cap. Each of these cases uniquely determines a vector. And now we'll see how to convert between these two for any arbitrary vector. So first we'll go from magnitude and direction to xy, meaning we are given a vector with magnitude a and making an angle theta with the x-axis. Now a has to be a positive number, theta could be anything between 0 and 360. So the vector a making an angle of theta with the x-axis means the magnitude and direction is a and theta. What are the x components for the vector whose magnitude and direction is a and theta? Well, that's quite easy. This would be a cos theta, the length, and this would be a sin theta. This is x, this is y, the unit vector here is I hat and here is j hat. So obviously the x and y components would be a cos theta I hat and a sin theta j hat. In the previous case we had the magnitude to be 6 and this was 30, so this was 6 by root 2 and this was also 6 by root 2. Meaning if the magnitude and direction is a and theta, then the vector can also be represented as a cos theta I hat plus a sin theta j hat. These two vectors are the same. A vector of magnitude a making an angle theta with the x-axis is the same as a vector which has an x component of a cos theta I hat and a y component of a sin theta j hat. So given the magnitude and direction of a vector, we can calculate the x and y components. Now we'll do the opposite. Given the x and y components, we'll calculate the magnitude and direction. So let's say the x component is capital X and the y component is capital Y. Right. Then what is the length of this line segment? That is root of x squared root of x square plus y square, which means from magnitude and direction we went to x and y. Now if we are given in terms of x and y components a vector with x I cap plus y j cap, then the magnitude of this vector is root of x square plus y square. And what is the direction? By direction we mean this angle. If this is theta, we get tan theta is equal to y by x, which means theta is equal to tan inverse of y by x. So this is it. These are the two formulas for the two representations of a vector. Given a vector with magnitude a and angle theta with the x-axis, it can be represented as a cos theta I hat plus a sin theta j hat. Given a vector with the x and y components as x and y, meaning the vector can be written as x I hat and y j hat, the magnitude of the vector will be root x square plus y square and the angle made with the x-axis will be tan inverse of y by x. So looking at this again, if we are given 3 root 2 I cap plus 3 root 2 j cap, then the magnitude will be root of this square plus this square, which is 6, and the direction will be tan inverse of y by x, which is 45 degrees, which is what we knew already. Here 6 and 45 gives me 3 root 2 I plus 3 root 2 j. Now why did we learn these two formats? Well, in the next two videos we learn operations on vectors just the way we know operations on numbers. We learn how to add two vectors, subtract two vectors, multiply a number with a vector, and even multiply two vectors together. And in all of those cases, we can do those calculations by having the vectors in the magnitude and direction form, or we can also do those same calculations by having the vectors in the x and y components form. Right? These are just two representations of the same vector. In some cases, the first form will be easier to work with. In some cases, the second form will be easier to work with. So in some questions, you will get a very quick answer if you convert all of the vectors in the magnitude and direction form and get the final answer. In some other cases, it will be much more convenient for you if you convert all of the vectors in xy component form and then do the calculations, whether it's addition or multiplication. And that will come with practice, in which case what is useful. Right now what is important is you should be very comfortable with me giving you a vector in one form and you being able to tell me the same vector in another form. Right? So in the next video we'll do addition, subtraction and multiplication of a vector with a number, and in the video after that we'll do the multiplication of two vectors, which you can do in two separate ways. Thank you.